Good morning. You had a nice weekend. Welcome back. So we have homework to do tonight. But yeah, just a reminder, you have homework to do tonight. Make sure you take care of this. So today, I want to relay what we're about to do to something what we did last time. So I want to remind you about what we did last time was we were classifying primitive Pythagorean triples. And so we classified all primitive solutions to a squared plus b squared equals c squared. We called those things Pythagorean triples, and by primitive we meant solutions, where there was no common divisor amongst a, b, and c. Anyway, what this led to, I'll just remind you, is formulas that looked kind of like this. So we had a was n squared minus m squared, b was 2mn, and c was n squared plus m squared for certain integers m and n. So n was larger than m here. They had GCD 1 and 1 even, 1 odd. So that was the full classification. So one thing I wanted to mention in brief is that, this was the whole thing we did about squares, like the Pythagorean theorem. A natural follow-up thing to consider after you study this equation is what happens if you raise the exponents. So you could say, what happens? What about solutions to a to the k plus b to the k equals c to the k? Let's say for k larger than 2. If you up the exponent and say, let's consider this instead. Okay. And this turned out to be a really famous and famously difficult question. But anyway, it turns out there are no solutions. So it turns out there are no solutions at all with positive integers, let's say. A, B, and C. Have you guys heard of this fact? This was a famous fact. So this is something that came to be known as Fermat's last theorem. So this is a theorem that has no place getting proved in a course like this. Okay, so it turns out it was super hard. Okay, but anyway, it turned out there's just no solutions at all. So it's a bit of a striking contrast with what happens when the exponent is 2, and we have loads of solutions that we can find. Anyway, so Fermat, as the story goes, I haven't been getting my stories too right in this class so far, but the story is something to the effect of Fermat in one of his notebooks, and this was probably in the 1600s or something. Claimed this was true and scribbled something down in the margin. I think I have a lovely proof of this fact, but it won't fit in the margin. Something like that. And so then anyway, people tried to prove it for 350 some years or whatever, maybe 300 years, I don't know, and they could not prove it, right? So people are quite skeptical that Fermat actually had a proof of this, or he probably had a flawed proof or something, and didn't realize that had a mistake. Anyway, so it was something that vexed a number of theorists for quite a long time, and became like a famous thing. And so just sharing it with you was part of the lore of number theory. Anyway, so it was I think anyway it was eventually settled in the mid-90s, 1990s, by Andrew Wiles. So this was eventually proved. By Andrew Wiles. And so I believe the year was 1995, if I'm not mistaken. it turned out to be, they use a lot of like fancy abstract machinery to sort this out. But anyway, I just wanted to point it out to you. We're not going to really talk about it. Something that is kind of true, which I could tell you about if you were interested, or like pass along some info outside of class if you were interested, is there is a way to at least prove this when K is 4 in a fairly low-level kind of way. It actually, can be done by using the theorem we had in class. Like if you're just going to work with 4 as an exponent. Because actually, if you have a solution to this when K is 4, these are squares of squares. But in particular, they're squares. So there is something going on with having a Pythagorean triple there. And that's how you could get the argument started. Anyway, okay, I'm just going to leave it there. But I just wanted to at least mention this. But we were going to go in a different direction now. So the next thing, continuing along though with Pythagorean triples, here's a question. So two questions. Well, I'll just ask one question. So let's consider the following questions. We'll find all primitive Pythagorean triples which have the following form. So what we're going to assume is A is 21, basically. So let's say if any exist at all, which perhaps there's a chance there's none. But anyway, here's a question one can consider. Okay, so let's suppose we want our A to be 21 and we just want to fill out B and C in such a way that we make a primitive Pythagorean triple. We'd like to know all the ways we could do that. And so this is then when our theorem becomes useful, because we know that all primitive Pythagorean triples fit into this form, right? So anyway, if you had such a thing, okay, so such an ABC, or such a triple, if you had one, it would, it's A is 21, so you'd have 21 is n squared minus m squared for some n in m, like over in our theorem. And then you have the formulas for B and C, for some m, n and m. N and m as in the theorem, with those extra assumptions. Relatively prime, one even, one odd. But anyway, then the game becomes like finding an n and an m that make this work, right? And so if you can find an n and an m that satisfy this equation, then you can put them in for B and C, and maybe you've got yourself a triple, as in question. Okay, so then what it comes to now is you have to look at this and say, well, okay, how can I write 21 as a difference of two squares, right? And so that is then, that is in fact just a number theory question that can be posed more generally speaking, which is, given an integer, how can you write it as a difference of two squares? Okay, so you need to write 21 as a difference of squares. And so this is going to be a general question that we're going to pose today and answer today, like given a number, how many ways can you write it as a difference of squares? Now, we'll focus on answering that in general in a second, but I guess I'll just point out to you that there's a couple ways you could do this with 21. In fact, maybe you know. Can you write 21 as a difference of squares? 11 and 10, yeah, right. So that's the bigger one, like with the larger numbers. Yeah, so if you did 11 and 10, right, that's one way. Let's write that down. So you could have, so this works with, I guess, n is 11, m is 10, right? So what you would have there, 11 squared minus 10 squared, that's 121 minus 100, and that's 21. So that is one way to do it. And then there's a smaller way to do it with smaller squares. But before we get to that, so what would this yield is in terms of these formulas, this would give us B is 2nm, 2mn, so that is 220, I guess. And then C is n squared plus m squared, so that would be 11 squared plus n squared, so that's 221. So this is one of these Pythagorean triples where B and C differ by 1. That was kind of like our first little recipe of building them, if you recall, always yielded things like this. So anyway, what this gives us is the triple, which you could verify is in fact a primitive Pythagorean triple, so that's 1. Okay, and so there is in fact another way. 5 and 2. 5 and 2. Yeah, that's good. Yes, it does. Sounds great. Yeah, 5 and 2, right? So 25 minus 4, right? It's 21. Yeah. Yeah, so also works. Right? Also works with n is 5, m is 2, right? So 5 squared minus 2 squared. Indeed, that's 25 minus 4, that's 21. Okay, so that will also work out for us. And that'll give us some smaller numbers and give us a different triple. Right? So if you wanted a Pythagorean triple, then you would have 2 times 5 times 2, which is 20. And then C would be 5 squared plus 2 squared, which is 29. So anyway, that would give us a different one, which is 21, comma, 20. Yeah, so anyway, that's, those are 2 ways. Now, those are actually the only 2 ways, but we're going to learn some things, so we believe that a little more enthusiastically. Okay, so, but there are no other ways. But so anyway, where we're headed and at the moment is if you wanted to answer a question like this, though, and if you wanted to change this number to something else, and you want to get all the ways you can do this, it's going to come down to all the ways you can write 21 as a difference of squares. Now, there is something that ought to be pointed out about what happened here is that the n's and the m's we got in these 2 examples were valid pairs for our theorem about primitive Pythagorean triples. Right? So what happened was they were relatively prime, one was even, one was odd. Okay, and that did guarantee it was primitive. So it could have been the case, by the way, that there was a way to write this number as a difference of squares where the n and the m didn't satisfy those, and then we might have gotten something not primitive. But these 2 did yield primitive ones. So we might encounter a situation like that later. But anyway, so we're going to actually just focus a little more carefully on this problem now, just as a general problem. So that's the main thing about the next section. The next section is just about differences of squares. Okay, and we'll just think of this as a little bit of motivation or like an application of knowing the ways to write something as differences of squares. Okay, so right. So we're going to consider the general question. So just given, let's say, a positive integer m, we'll just call it, we'll ask the question, how many ways, if any, let's say, can we write m as a difference of 2 squares, and in this discussion we'll call them x and y squared. Okay, and so here, the question we're really asking is with x and y being integers. Okay, so anyway, the first order of business is actually going to be to observe that there are, in fact, some numbers that cannot be written at all as a difference of squares. And we want to know which ones this applies to, right? Like, so which ones are there no ways at all? And then for the ones for which it is possible, we want to know how many ways is it possible, because like in this example, there could be more than one. Okay, so anyway, here is the first fact. So suppose we have a positive integer. And the statement is that m can be written as a difference of squares okay, if and only if. Okay, so where this comes from, I'll try to say it before I finish the thing, can be kind of observed from these things we were doing in our proof last time about looking at squares of integers and making claims like how, if you square an even number, it's a multiple of 4, right? And if you square an odd number, we said something which was, in fact, it's 1 more than a multiple of 8. Okay, that implies, by the way, it's 1 more than a multiple of 4. So if you just focus your attention on multiples of 4. So what could happen when you square things is either you get a multiple of 4 or you get something that's 1 more than a multiple of 4. Okay? And so if you start thinking about multiples of 4 and that kind of stuff, it could be like that this is a multiple of 4 and you subtract 1 more than a multiple of 4, and then you get something 1 less than a multiple of 4, which is like 3 more than a multiple of 4, like remainder of 3 would be divided by 4. That could happen. You could have like 2 even things, then this is a multiple of 4. And you could also have a scenario where, this is, like if this one was odd, that one was even, this would be 1 more than a multiple of 4 minus a multiple of 4, so it's 1 more than a multiple of 4. But what cannot happen in any possible way is you can never get a result that's 2 more than a multiple of 4. Okay, if you just are only allowed to work with something that's either a multiple of 4 or 1 more than a multiple of 4, and you subtract. So that's essentially the case that is just impossible, and it's the only case that's impossible. And so anything that is even but not a multiple of 4 is essentially, these are the bad ones. So odd numbers are all going to be okay, and anything that's a multiple of 4 is going to be okay. Okay, but it's just the evens that are not multiples of 4 are the ones that are excluded. So if and only if m is odd, or m is a multiple of 4. That is turns out to be the condition to know whether or not it's just possible at all, which is also saying nothing about how many ways is it possible, just that there's at least one way. Okay, so let's just investigate this. Okay, so this is an if and only if thing, so there are 2 directions of the proof. So I guess where we'll start with is explaining why these numbers below, odd numbers and multiples of 4, we'll explain why they can be written as a difference of squares. And here's the first observation. Okay, and the first observation is just to consider consecutive squares. So if you were to consider, say, the numbers n and n plus 1 and looked at the difference of their squares, just consider what happens whenever you, what happens when you take consecutive squares and subtract them. And algebraically, this works out to be 2n plus 1. Okay, and that what's on the right-hand side is just an arbitrary odd number. Okay, so if you turn it around and say, well, if I start out with an odd number, I could write it like this, and therefore I could write it like that. So the point of what's written right here is this shows that any odd number is a difference of squares. Okay, so any odd number can be written as a difference of squares. Okay, so there you go. And Okay, that addresses the odds. Now what about the multiples of 4? This just comes by doing something similar, but leaving a gap of 2 between the things that are getting squared. So next, note that if you were to say, consider what happens if you take a difference of these kinds of squares. So if I have a difference of 2 between the things getting squared, if you look at this thing and work it out and simplify it, what you get is the n squareds cancel, the 1's cancel, and you're left with a plus 2n minus a negative 2n, which is a 4n. And so that's an arbitrary multiple of 4. Right? So this shows any multiple of 4 is a difference of squares. Okay, in this way, like for example, if somebody just said, well, what about 20? Well, 20 is a multiple of 4. It's 4 times 5. So if you put 5 in here, you have 6 squared minus 4 squared. And 6 squared minus 4 squared is indeed 36 minus 16, it's 20. But that's just a recipe then to take any multiple of 4 and write it as a difference of squares. So anyway, what this proved is the backwards direction of the if and only if. Right? So if m is odd or if m is a multiple of 4, we've shown they are differences of squares. So now the converse is to just take some arbitrary integer, which is a difference of squares, and explain why it has to be either odd or a multiple of 4. Okay, and I mean, one way you could argue is what I was kind of saying out loud, or why these certain numbers are getting excluded. But there's a different argument that we'll give. So conversely, suppose we have m is a difference of squares. Okay, and the main thing that we're going to be using in this section to say anything useful at all is just the difference of squares factorization. Okay, so if m is x squared minus y squared, right, that means that m is the product of x minus y with x plus y. Okay, and that's going to be something we'll always be considering then. Okay, and so the thing about x, these two factors, x minus y and x plus y, and this is something you may need to meditate on to make sure you believe 100%. But the thing is, these two factors, these two numbers, if you consider them for the numbers which are x minus y and x plus y, they have to have the same even or oddness. They're either both even or they're both odd. Okay, so these are either both even or both odd. Okay, we're not talking about x and y individually, but rather like the sum and the difference. And so if you so and part of the point is minuses make no difference when you're talking about even and odd conclusions like this. But anyway, if you want to just, the thing is you want to make sure you understand this point. And if you need time to understand this point, you want to think through it deeply. What you need to just consider are all the possible cases of x and y. And so there's 4 cases between x and y themselves, which are like, x is even or odd, y is even or odd, and there's 4 possibilities for combinations of that. But just think through them all each time, and like for example, if x is even and y is odd, then what happens is an even minus an odd always gives you an odd. But an even plus an odd also gives you an odd, so they are both odd in that case. So this will be true no matter what you start with. So this is a key important observation that we'll use in this to answer our questions here. Okay, but anyway, what it means for us right now is once you believe this, there's 2 cases for what's happening above. They could be both odd, right? So if both are odd, then what happens is m being the product of 2 odd numbers is odd, right? So product of two odd numbers is always odd. That's a little exercise if you don't believe it for some reason. But then what happens if they're both even? Right, so if both numbers are even and they're getting multiplied together, then each has a factor of 2 in it, and then consequently there's two factors of 2, so there's a factor of 4. Okay, so each is divisible by 2. So what happens then if you factor out 2 of each one is you factor a 4 out. So 4 divides this thing, which is m. Okay, so that tells you that if you have something that's a difference of squares, it has to be odd or a multiple of 4. Okay. And so that is the forwards direction of this if and only. Okay, and so that kind of completes it. So that's the end of this proof. Now, it doesn't really, we didn't answer our main question yet, which is how do you find ways to write a number as a difference of squares, but this at least tells us which numbers can be ruled out from the discussion. But what is, something we got from this proof is that if m is a difference of squares, that leads to a factorization of m into a product of two integers which have the same parity. So that's what I'm going to use that word a little bit. So what we're saying, when we say they're both even or both odd, another way to say that is they have the same parity. So the way we're using that word is the parity of an integer is whether it's even or odd. Okay. So a number, so a difference of 2 squares gives you a factorization of m into a product of 2 integers with the same parity. Okay, and then we want to know if we could turn that argument around and say, conversely, if we can factor m as a product of 2 integers with the same parity, can we turn that into a difference of squares, basically? So let's put the ideas together, explain where it comes from. So anyway, what we just saw that writing m this way, having m be a difference of 2 squares, gives you a factorization of m into a product of 2 integers with the same parity. That is, they're either both even or they're both odd. So now let's turn it around and say, well, conversely, what if we start a discussion with the factorization of m into a product of 2 integers with the same parity? So conversely, suppose m is a product of 2 things, let's just call them u and v. And we just found some factorization, and u and v have the same parity. Okay, so the idea is, like for what is about to happen, is you want to think of like u as though it's one of these factors and v is the other one. So I think we'll actually probably think of u as the bigger one. So like think u as x plus y, and v is x minus y, and you want to know how to find x and y from that situation in terms of u and v. So the sort of thing we're going to be thinking about, I'm just writing this on the side as a little scribble, is you want to kind of think of like u as x plus y, v is x minus y, and think of that like a system of equations. You want to solve for x and y in terms of u and v. Okay, and it's possible to solve that thing and express x and y in terms of u and v. And if you do figure that out, the way it works out is this. So back over here, if you let x be u plus v over 2 and y be u minus v over 2, both of which are integers, by the way. Okay, because they have the same parity. So if you add or subtract two things with the same parity, you always get an even. Right? Sum of two odds is even. Difference of two odds is even. So on. So you can divide it by 2 and get an integer. But these are the x and y that'll give you a difference of squares. So what happens here, and this is something we can just prove with a little bit of algebra, is that if you consider x squared minus y squared for this x and that y, right? So you have u plus v over 2 squared minus u minus v over 2 squared. Okay, let's just do the algebra on this to see what it is. Okay, so this is going to be u squared plus 2uv plus v squared over 4. And this one is u squared minus 2uv plus v squared over 4. Okay, if you combine those things together, there's a lot of cancellation. U squareds cancel, v squareds cancel, and you get 4uv over 4. That's it. And so that's uv. But we just started out our discussion by saying m was uv. So this is m. Okay, so starting out with the u and the v, you could build an x and a y this way. And this proves that x squared minus y squared will really give you m. Okay, so it gives you a way to write m as a difference of squares. So what we're seeing on here are sort of two halves of the story. So over here on the left half, we said, like, if it's a difference of squares, then we get a factorization into a product of two integers of the same parity. And here we're saying, if instead you start with the factorization into a product of two things of the same parity, then you can build a difference of squares for m. So it actually sets up a one-to-one correspondence between these two things. So the ways to write m as a difference of squares is actually in correspondence, one-to-one correspondence with the ways to write m as a product of two integers of the same parity. Okay, and the point is that's easier to think about and understand all the ways that's possible. So anyway, here's our conclusion from this little discussion. Sort of kind of informally just explained everything that goes into this. So there is a correspondence, say one-to-one correspondence between the following two things. On one side, you have all the ways you can factor, factorizations of m into a product of two integers, say uv, we'll say first, we'll say uv have the same parity. And we'll just tack on the condition u is the bigger of the two, or maybe they're equal. And that the ways to factor m in such a way is in one-to-one correspondence with the ways to write m as a difference of squares. So ways to write m as x squared minus y squared. This is not that important of a point, but we're not considering negative x's and y's, which would, because it wouldn't yield anything different. Okay, so anyway, the way the correspondence goes, and we're mostly interested in pushing it forward this way, is that given a u and a v, right, so given a way to write m as u times v, where that goes over here is that m is u plus v over 2 squared minus u minus v over 2 squared. And so this is the x, this is the y. So out of a u and a v, you can build an x and a y in exactly this way. And the harder question on the surface was, how do you find all the ways to do this? The easier question is, how do you find all the ways to factor m into a product of two integers of the same parity? At least that's certainly an easier question when you just have a number like 21 or something. Okay, so for example, going back to 21, we found all the ways to write 21 as a difference of squares, and I told you that was all of them, but maybe you didn't believe me. But anyway, once you have this, this will tell you how you can find them and know you have them all. So if you wanted to, as an example, find all ways to write the number 21 as a difference of squares, what you need to do is consider all factorizations of 21. So consider factorizations of 21 as u times v, as over here, where let's say u is larger than v or equal, and u and v have the same parity. Okay, now the parity issue is not much of an issue if the number is odd, because you're not going to have two evens there. That wouldn't even make sense. Right? So the factors u and v are necessarily going to be both odd here for the number 21. So we don't have to worry about that right here. But basically, you just say, how many ways can I factor 21? And this is not like necessarily involving primes or anything. Just factor 21 as a product of two positive integers. Right? So possible factorizations, would be things like 7 times 3, but also 21 times 1 is valid here too. Okay, so you consider all the possible ways, and I'll just make a little table because there's not too many here. But, for example, you could take 21 times 1. That counts as a factorization of 21 into a product of two integers. And then what you can get out of that is you get an x and a y, according to these formulas. We're assuming u is the bigger one, by the way, so that when we subtract them, we don't get a negative. So anyway, you can consider these. And for 21 and 1, if you add them, you get 22, and if you divide by 2, you get 11. And if you do this one instead, if you do 21 minus 1 over 2, that's your 10. And so your difference of squares over here. In the last column is we're showing that we found 21 is 11 squared minus 10 squared, which is one of the ways we had. And then you say, okay, great, that's one. Then you say, what other ways can I factor 21 as a product of two positive integers? And the only other way is 7 times 3. There's no other ways to do that. But then from u being 7 and v being 3, right, put those into this. This is going to be 10 over 2, which is 5. Right, and this one is going to be 4 over 2, which is 2. And that's where the 5 and the 2 come from. Let's say 21 is 5 squared minus 2 squared. Okay, and so now, since there are no other ways to factor 21, we know there are no other differences in squares. That's the full story. Okay. Good so far? So let's consider something that's just another example. A multiple of 4. Right, so a multiple of 4 can be written as a difference of squares. This wouldn't fit into our Pythagorean triples discussion so well, but it's still just a difference of squares question. So you could say, find all ways to write the number 40 as a difference of squares. Okay, and so what you're supposed to do is consider factorizations. Right? 40 is u times v. Okay, so we'll make a little table like we did. Okay, so we'll have x and y. Okay, so anyway, right off the bat, I'm going to write something that's not good. But the one factorization of 40 is 40 times 1. Okay, but this is not something we can use for our purposes because this This is not a factorization in which the two factors have the same parity, right? 40 is even and 1 is odd. So this is actually like no good, not the same parity. I'm like Fermat writing in the margin here, but sorry. We don't have the same parity, so this is no good. Nothing comes out of that, okay? So, but still, what's a natural thing to do before you think about that is maybe just list all the factorizations of this number into a product of two integers. Like, for example, you could just say 20 times 2, and probably it's more natural to think of the small divisors and you'd see what factorization. So 1 is a divisor, 2 is a divisor, 4 is a divisor, and 4 times 10 gives you 40. 5 is also a divisor. 5 times 8 gives you 40. And there's nothing in between 5 and 8. That's kind of all the divisors of this thing. So anyway, this last one that popped out here is also no good for us, right? There are no, those do not have the same parity, so we'll cross those out. But these two factorizations in the middle are the good ones, and they're factorizations in which both things are even. And so we can put them in and we'll get an actual difference of squares. We'll get two ways to do this. So 20 and 2 is 22. Okay, over 2 is 11. And then if you subtract them to get y, you get 18 over 2, which is 9. Okay, so what you get over here is that 40 is 11 squared minus 9 squared. Which you take a moment, that's 121 minus 81, which is exactly 40. Okay, and then this will give us something different. So 10 and 4 is 14 over 2 is 7. But the difference is 6. Right, and divided by 2 is 3. So that'll give us the second way, right? So that's 49 minus 9. Right, so 7 squared is 49 minus 3 squared is 9. So that also checks out. But that's it. There's no other ones. Okay, that's how this gets used, and it's not much else to it. That's what you would do. But so yeah, if you start out with something odd and you try to do this, the parity issue is a non-issue because you would never have an even factor. But if you start out with a multiple of 4 and play this game, you have to be careful to exclude certain things in which the parity doesn't match. Okay. So, is that okay? All right. So I want to just do in closing. Let's do one more example, but kind of let's connect it back to this primitive Pythagorean triple stuff again. So let me do it over here. So let's consider the problem of, I'll write it here. Let's find all primitive Pythagorean triples where A is 45. So the A of the Pythagorean triple is 45. So we're going to have 45. 45 is supposed to be n squared minus m squared, and B is supposed to be 2mn, and C is supposed to be n squared plus m squared. Those are the Pythagorean triple formulas we have. And there are some requirements for n and m, right? Like, remember from the theorem, one is even, one is odd. Opposite parity, right? And they're relatively prime. But the way you start is with this. So to answer this question, you start by focusing on this and say, what are all the ways I could write it as a difference of squares? Right? So first, write 45 as a difference of squares in all possible ways. Okay, and so just maybe a little less organized if I don't have the table now. But what are all the factorizations of 45? Right? You could do 45 as 45 times 1. Right? That would be 1. That's a u and a v. Okay. So what this leads us to is you have to consider their sum over 2 and their difference over 2. So this will give us, one of them looks like this, call it N, and M looks like this. So this gives us 23 and 22, right? That's our N and our M. So that's a valid way to write 45 as a difference of squares. And then N and M satisfy all the relevant conditions, so opposite parity, relatively prime. So this will give us a Pythagorean triple. Okay, so this one will give one. And what will happen here is if you work this out, B is 2 times 22 times 23, and C is going to be the sum of these squares, which I'll just tell you the answer to these. Okay, so that out of this pops a one primitive Pythagorean triple that looks like this. Okay, and then you say, well, what else can I do with 45? Right, so 3 is a factor of 45, so you could factor out a 3 and then times, I guess, 15. Okay, and you can figure this one out. So what happens here is you can find the N and the M to write it as a difference of squares. Sorry, these are like our X and our Y. They're just called N and M over here. But you could figure these out. And the one of them is 9, the other is 6. And what happens here is, just note, I mean, this is saying 45 is 9 squared minus 6 squared, which is true. It's true. So it's a way to do this, but it's not an appropriate candidate into this primitive Pythagorean triple theorem. Okay, the problem with this N and this M is they're not relatively prime. Okay, so these are not relatively prime. So what happens is, you can check this, is they don't give a primitive triple. Because whatever you get is going to be divisible by 3. But anyway, they don't satisfy the conditions of the classification theorem. So that, you get a difference of squares, but it's kind of a dead end as far as one of these is concerned. Okay, and then just the rest of the story, though, is there's one more way to write 45 as a product. I think it's 5 and 9. And these are the only factorizations, I believe. So this leads to just one more thing. And here, you do 9 plus 5 over 2, you get 7. And if you do 9 minus 5 over 2, you get 2. And indeed, 7 squared minus 2 squared is, sure enough, that's 45. Right, but 7 and 2, those fit into this theorem. They're opposite parity, relatively prime, so you can put them into this and make a triple. So out of this, this is a good case. Let's just find what the conclusion is. Right, so B comes out to be 28. And C comes out to be 7 squared plus 2 squared is 53. Right, so out of this one yields 45, 28, and 53. Okay, but there are no other ones. That's the point, is you found them all. And that's the way you can tackle this kind of a question, at least for any odd number A.